As mentioned before, here we're going to talk about robot engineering principles. If you want to learn more about these robot engineering principles, we're getting them from this reference, which you can find at the end of this lecture. So robot engineering principle number 1 is understand by building. So of course this is manifested as the incremental growth of complexity of cellular systems, which is what the historical record shows. So exactly the 3.8 billion year history of life shows progression from simple to complex. Robot engineering principle number 2. Agents should be designed for emergence or adaptation. So put simply, the environment should shape the agent's behavior. So if you're building a robot, you should be able to interact with the environment and then change the behavior accordingly. So obviously, biology does this, but not just reacting to the environment. Of course, any robot that you build will have to sense its environment and then act accordingly. And biology does too, of course, but in biology, biology or the cell has long-lasting changes because of its interaction with the environment. These could be epigenetic changes. These could be evolution type changes where you have survival of the fittest, etc. Robot engineering principle number 7. Agents should be autonomous, self-sufficient, and realized as physical systems. Of course, you can't have a robot that's just some set of pixels on your computer screen. That would not be a robot. It would have to be a physical system. Of course, cells are physical systems. Cells are essentially autonomous, although they can work together. They are self-sufficient. In a multicellular organism, you would count that organism as self-sufficient and autonomous. So it's obvious that the cell or a multicellular organism meets these criteria. So let's imagine, for example, the criteria necessary for life or for a cell. What things does a cell have to have? It has to have a membrane. That's a way to separate itself from non-self. It has metabolism and self-replication. So other robot engineering principles that you can find in that reference number 4, they reprise others that we've seen already, such as redundancy, interaction with the environment, and parallelism. So what are the implications of the fact that the cell embodies so many engineering principles? Well, first of all, I think it should be obvious that the cell would embody engineering principles. As I mentioned before, anything that we build, if it doesn't adhere to these engineering principles, then it will fall apart. And of course, it's clear that biology has not fallen apart, and so of course, why would not the cell also have to adhere to these engineering principles? But what are the implications? I think the first implication is that biology will inform engineering. So as engineers, if you study biology, you will learn new engineering principles. Since biology has been around a lot longer than we have. Also, biomimicry. So we can look at the biological world and say, wow, that's really cool, and that's a really cool design for that purpose. Why don't we use that too? And that would not be a new engineering principle. That would be a new application of engineering. Also, engineering will inform biology. So for example, if you are a biologist and you are studying a particular biological pathway, it may not make sense what that pathway is supposed to be doing. But from an engineering point of view, you might say, you know what, because of trade-offs, or because I've identified this performance objective, or because of multi-performance objective optimization, or because I know that this negative feedback loop usually constitutes robustness to the system, etc., engineering will inform your biology. So it could provide explanations of phenomena, and in addition to that, there could be an expectation of engineering principles. For example, you might say, look at a particular biological system, and you might say, well, if man were designing that, this would need to adhere to such and such an engineering principle. I expect there to be a particular pathway in there that adheres to that engineering principle. And then you can go and look for it. So it could be predictive. Another implication is that biologists should learn some engineering because it's so important. And of course, another implication is that engineers should learn, learn biology. And that's what we're here for. Okay, so the references that I promised at the end, and that would be the end of our lecture.